Next up, we have Tatiana Miti.
Hello. Thank you for putting together this awesome conference to the organizers. And today I'm going to talk about stromal effects on the remission-relapse dynamics in triple-negative breast cancer. Which one works? Complicated. Complicated. I think I'm technologically challenged. Can somebody help me? Oh, here we go. Okay. So first I want to say that the project, actually the masterminds behind this project is a game theorist, a cancer biologist, and then a physicist. And I was brought just to do the work so the story is actually, what I'm going to tell is actually a story about stromal effects, and specifically it's about cancer-associated fibroblasts. So as a lot of us know here, and Andrew has told yesterday, cancer-associated fibroblasts can do a lot of things for the tumor cells. They can either enhance their proliferation, they can actually mediate death, or they can be neutral or basically do nothing for the tumor cells. So in triple-negative breast cancer, it has been shown that in patients, the fraction of stromal component actually correlates with the survival. So it's a negative correlation. Actually, the more you have, the lower chances of survival you have. At the same time, in, of course, cell cultures, it has been shown that if you actually are either co-culturing or you're using the culture media during treatment, during chemotherapy, you can actually partially rescue cells from death. So basically then the goal is, how do we make sense of this and how do we understand what is the contribution of purely just fibroblasts on the remission relapse in triple-negative breast cancer? And at the same time, if we identify this, how can we actually disrupt these effects to have a better outcome? So the project overall was, it's a flow. So the data that we primarily envisioned is either from patients or from mouse xenografts. And then because it's paracrine factors, it's secreted, there's a spatial component in it, so we will have to do some spatial analysis. For that, you need a spatial point pattern, and from there, we will use an ABM to basically look at these effects. So a little bit, I know that Andrew said that I'm going to talk a lot about spatial stats. I will actually not, I'm sorry. But here is a quick overview. We have a histological sample. We use an AI-based program, Aphoria, to actually extract different components of the tissue. So we can extract necrosis, macronecrosis, micronecrosis, and most importantly, we can actually extract the XY coordinates of the centers of nuclei of each cell. And the cells are either proliferating or non-proliferating tumor cells. So then we can successfully get a point pattern out of it. The stroma component is not a point, but we can extract the polygons and then pixelate the polygons and then create a point pattern from there. So this is the most spatial stats. But I put together basically a pipeline for some spatial statistics to extract the intensity. First of all, is to see if there is any spatial interaction between stroma and tumor cells, both proliferating tumor cells and non-proliferating tumor cells, because we think fibroblasts enhance the proliferation. So the proliferation is the marker that we're using. So first is to see if there is any interactions. And then we use the radial distribution function for the physicists. For the other ones is cross-correlation function. We use that to look at the local fluctuations in density with respect to stroma distance. And then to look at the actual strength of the interaction with the J function, which is basically just a non-parametric ratio of the empty space function and the nearest neighbor function. And then the coolest is the resource selection function, which is just one of the many type of population distribution functions that actually establish the stroma as a covariant for the distribution of the proliferation tumor cells. So quickly, initially we did it was a pilot experiment to see if we can identify whether there are any spatial interactions in these systems. Here we see that actually even in absence of treatment, there is an interaction between the stroma and tumor cells. It's not too pronounced in absence of treatment, but actually becomes much more pronounced. I don't know if you look at the resource selection function, that peak for the proliferating tumor cells, actually now it becomes more prominent, while for the non-proliferating tumor cells, which is BRD negative, is the marker for proliferation, it's actually, you see that it flattens out. So there's no preference with respect to stroma of how they are distributed. So then after that, we put a bigger experiment together where we do take mice, we treat them with 4 rounds of chemotherapy, and then we do the same thing. We do the data analysis, and then we build an ABM. This is the on-lattice ABM we're looking to. We're using to look at the system, and basically it's nothing fancy. It's just a cell can divide, die, or move, and that is also. It's all depending on how its proximity to stroma. So it's everything. It has to be checked how far away. So first, we really wanted to calibrate properly the system, and we're mostly interested about what is the spatial distribution of proliferation and death. So for that, initially, basically, bulk. We use the BRDU, which is actually a marker for just the synthesis, cells that are just in the synthesis phase. So they are actively proliferating. So from there, you can actually get a proliferation rate, not a growth rate, but actually a proliferation rate. And we see that we have it for the treated and untreated. It doesn't really matter how many cycles it has. It looks like it's the same, regardless of how far along you're at the treatment. And then, of course, for the spatial distribution, I use the radial distribution function, which can be converted into a probability density function to basically sample, to say, give a probability of proliferation to a cell as a function with a function of distance to stroma. For the death, we see that apoptosis, which is just the programmed death, it doesn't really matter whether you apply treatment or not, and it doesn't have any spatial dependence with respect to stroma. I did the same thing to look at actually during the treatment with micronecrosis areas would vary with respect to the stroma, and they don't. So when I assign the rates for the death, it doesn't really matter with respect to stroma. A little caveat here is that the death actually it's extracted mostly from, if I need to actually put a number in it, I actually do it from the cultures, the cell cultures, because the mouse model is not the best representation of actually the human model. And for migration is a wild beast. You will see that in vitro people do all types of measurements. I haven't found one in vivo. But what I do here is, because I have some constraints about how much micronecrosis I have, what is my proliferation, and what is my spatial distribution, I just calibrate this to the migration rate to basically recover what I see in the tissue. So it's a little bit of playing around with the migration. So here are some results. First, what we do is we're interested in there's this protocol usually done with in vitro, where they look at the death at 4 days, basically. Like they apply chemotherapy and then they look, what is the death rate at 4 days? So initially what we did is like, we need to see what is the killing rate of the drug in absence of any stromal effects in order to see how stroma actually affects or how actually is rescuing this the tumor. So we did a scan of the killing rate, and actually what you see is that if death due to chemotherapy actually occurs fast, you need a high killing rate, which is non-intuitive, a high rate to actually kill the tumor, or I mean to eliminate the tumor completely. Before you freak out, that's not a Schrodinger cat situation. That's the average of 500 simulations. That's why you have negative like fraction of cells. Okay, so then if now we add stromal effects, right? If now the stroma starts to enhance proliferation, you see that you don't really need a lot of bias, you don't really need a lot of paracrine factors to rescue the tumor, which is a little bit unnerving. And I know that that 3% there, it's not much, but imagine that this is just a very small portion of the tumor actually, right? So if this is a cumulative effect, then it's fairly scary. But actually, when you look at the in vitro data, you see that the cytotoxic effect, of course, it's way much longer. And we try to recapitulate that also in the ABM, and that, of course, it's no surprise that having a prolonged effect, you don't really need that much efficiency from a drug in order to actually kill or eliminate the tumor in absence of any stromal effect. But the moment you actually start to add some effects, for the prolonged cytotoxic, you actually need, on one hand, you need way much more stromal effects in order for this effect to be evident. The interesting thing is that if your killing rate is not high enough, right? If your drug is a little bit failing, then just a little of a very small percentage bias in your proliferation from stromal effects actually leads to a 90% relapse, which is, it's fairly scary. So then, of course, we know that stroma, well, we thought that stroma does cause all of these effects. So there's a way of basically interrupting these mechanisms. And of course, the three main mechanisms would be to mess up with the stroma, right? And see if I'm now decrease the radius of this effect of the paracrine effect, which is done, there are actual drugs that do that. Would I be able to eliminate the tumors? And it looks like, you know, you have to do darn well. You have to really, really reduce that stroma radius in order to cure, like eliminate the tumor. You have a better chance at actually decreasing the proliferation rate and or increasing the death rate, which both are options in the clinic. And of course, the combined effect is even better. So this is, thank you. Welcome to Florida. Don't forget to look for alligators on your porch. That it's Moffat over there. No questions. Cool.
I know it's hard because lunch is
I know.
waiting outside the door. You know, she's Tatiana down there.
And I'm hungry too.
All right, she's hungry too. Okay.